Um, there we go. Welcome, everyone. This is a special DP1 science preparation seminar. And I'm your host, Jeff Carlin. I'm a member of the community science team at Rubin. I think I saw Gloria Fonseca Alvarez here also. She's another CST member, but there are about a dozen of us. We are the folks who facilitate events like this. And before continuing, I want to make sure I share the link to the slides for anyone who wants. Okay, so let's get going. I have a lot of material, but I think we can keep things somewhat informal. So feel free if you have questions at any time, raise hand or put it in the Zoom chat. I'm happy to take questions at any time. So I have a few announcements at the beginning. I'm going to do a short presentation just about the LSST data products. We're sort of focusing on time domain science, but if you have questions that are not related to time domain science, but just more generally about the data products and the survey, those are welcome, of course, too. And then we're going to do a tutorial where we demonstrate the use of both the portal and the notebook aspect. So if you would like, you can log into data.lsst.cloud if you have an account already set up, and follow along in real time. It's also fine if you want to just watch. Totally cool. And then we'll do my best to leave question and answer time at the end. So I shared the link to the slides in the meeting chat. The third slide is this one that gives you instructions for how to set up for the hands-on tutorial. In particular, you need to clone this repository, and this gives you actually, let me back up and just copy paste that into the chat as well. This is the get clone command that you'll need to copy over the notebook that we're going to use in a little bit. So this has instructions for how to do that. Again, this is the third slide in the slide deck that I shared. Oops, sorry. There we go. Okay, so just some links. There are a lot of handy links in the slide deck, so I encourage you to go ahead and grab that if you want all these links to keep track of. The link to get an account, if you haven't already, on the Rubin Science platform is at rsp.lsst.io. There are some links here describing the data sets and linking to a lot of tutorials and information about the Data Preview 0, which is the simulated data set that we've served to users, and that's what we're going to be using right now. And of course, our website for general information for scientists is rubinobservatory.org, and there's a For Scientists page. And the community forum, community.lsst.org, I encourage you, if you don't already have one, to create an account there. That is sort of like think of it as like Stack Overflow, but for Rubin. It's a place where you can ask whatever question you might have. Hopefully the knowledgeable folks from the community will chime in with answers. But if not, staff like the community science team are always monitoring as well. It may be a long journey for many of the folks who are on this particular call, but if you're interested in Tucson, Arizona, in the US, we are having our annual Rubin Community Workshop coming up in late July. It has a limit of about 250 people. Last I heard, it was already over half full. So if you're interested in attending, do consider registering. We also have coming up Rubin Data Academy, which is a fully virtual event where we spend a few days in focused sort of learning of how to use all of the the tools and work with the data sets that Rubin will be providing. There's an announcement, sort of a save the date, that has been posted on the community forum that I put a link to here, and the official announcement and registration form for this will be available very soon. But we know it's going to take place during the week of June 23rd. So do set aside time for that if you are interested in doing sort of an intensive learning experience about all of the resources, Rubin resources. And we do have weekly science assemblies, again, for folks who are in Australia or East Asia. It may be difficult to make these, but we do record all of them and post the recordings. So the next science assembly, which is next Thursday at morning, my time, California time, is about actually a link frameworks tool that's being developed called Hyrax to enable machine learning discovery in Rubin data. And if you want to see the list of Rubin science assemblies and links to the recordings of them, go again to rubinobservatory.org. There is a Rubin science assemblies page under the events and deadlines. I just mentioned link frameworks. This is a project to develop software and algorithms in collaboration with the community to enable science with the massive LSST data set. There's a list here of a few of their projects. And this is just to advertise that they have weekly office hours that you are welcome to drop in if you have any questions. Likewise, if you have any questions or comments about Rubin LSST data products or data, I guess the RSP and things like that, the Rubin Users Committee is charged with gathering feedback from the community. So that we list here the 12 members, current members of the Users Committee, and how to reach out to them. And they always welcome feedback from the community. So if you have anything you would like to raise, do consider contacting our Users Committee. If you want to get involved in LSST science, but you're not quite sure where to start, one good place to get started is the LSST science collaborations. There are 8 of them: active galactic nuclei, dark energy, galaxies, informatics and statistics, solar system, strong lensing, stars, Milky Way and local volume, and transients and variable stars. And of course, there's overlap between a lot of these, but they are a great place to get started, start working with a like-minded community. But of course, you don't have to join a science collaboration to do science with the Rubin data. It's just an opportunity, should you like to do so. And again, on our website, rubinobservatory.org, on the scientist webpage, there's a science collaborations page that gives you more information about them and links to all of their sites where you can you can join those science collaborations. Okay, so I'm going to briefly introduce some of the qualities of the Rubin LSST data and our ecosystem that you will need to know to work with the to do transient science, I guess. But of course, this is relevant to static sky science as well. It's relevant to almost anything. I'm focusing on transient science, but of course, if you have questions about galaxies or whatever else you're interested in, do feel free to ask. So I trust you're all at least somewhat familiar with the survey, but just a reminder, this survey will provide a very high cadence with a wide field of view, meaning that the entire southern sky will be surveyed roughly every 3 nights in 6 filters. High resolution data with a pixel scale of 0.2 arc seconds and generally good seeing at the site should provide excellent image quality and deep sensitivity, so a limiting magnitude of about 25th magnitude in G-band per visit. And then, of course, this is going to take place over 10 years, so you're going to have an extremely long baseline for light curves. And so this enables an unprecedented study of transients and variables, millions and millions of them. What types of things, astrophysical objects, are transient or variable? Well, a lot. I love this diagram showing this variability tree, which is basically splitting things into things that are intrinsically variable, meaning, say, pulsating stars, active galactic nuclei, versus, extrinsic variables, meaning like things that are eclipsing stars or rotating asteroids or things like that. But you can see there's a wide variety of things, from supernovae to all the types of variable stars to asteroids and all kinds of other objects, AGN, et cetera. So it's important for a lot of science cases to understand how to work with the time domain data set. So how will we find transients and variables with this data set? One key aspect of the survey is the difference imaging analysis. So you'll see this DIA abbreviation quite a bit. That's difference imaging analysis, meaning basically you have a reference image seen here in the center. So this is a template image that's been built up from a lot of high quality images in this field of the sky. And then you take a new image, that's your science image here, which is shallower than your co-added reference image. But you take this new image, you scale them appropriately, subtract the reference image from the science image, and are left with this difference image. And here you can see this is an example from the ZTF survey of a supernova here in this galaxy. And then we run detection and measurement on these difference images. Here's another example for a variable star. So again, you have a reference image, you subtract that from the science image, and you see there's still flux left, meaning this got brighter. So you can detect the brightening of that star. So this process of difference imaging and detection and measurement on all of the difference images is going to be done within 60 seconds of readout of every exposure. And then alerts will be sent worldwide, alerting you of all of the millions of transients and variables that were detected. And so those are distributed via alert brokers. And so these alert streams are served to 7 full stream alert brokers. They're listed over here on the right side. They each have their sort of specialties, and mostly tied to different sort of science drivers. But those are the software systems that take the massive fire hose alert stream that we are serving, ingest it, and do some massaging to serve those alerts in a way that you as a scientist can sort of mine those for follow-up. So I mentioned the science collaborations. One in particular is the transients and variables science collaboration. As I mentioned, there's a lot of overlap. Of course, there are a lot of people like myself whose primary science collaboration is the star's Milky Way local volume, but I'm interested in variable stars. So there's a lot of overlap between different science collaborations, but I wanted to highlight the transient and variable science collaboration in particular. If you're interested, do reach out. And there is also a link here to their roadmap, which is an extremely detailed document that tells you about all of the science and the data products that they're going to generate. And they have a lot of subgroups. You can see them listed here in this diagram on the right. Anything from supernovae to microlensing and pulsating variable stars and also equity, diversion, inclusion, et cetera. So do check out TVS, the Transients and Variable Stars Science Collaboration, if you're interested. Okay, and then I want to quickly run through what are the types of data products that we will be making available for you to use for your time domain science. Before I dive into that, I want to pause and see if anyone had any questions. Okay, let's dive into the data products. So as I mentioned, there are data products being generated on various scales. The first, which I discussed already, was the difference image analysis, which happens within 60 seconds of a new image being taken. We do the subtract the template image off, run detection, source association, everything on the difference images, and distribute those worldwide to alert brokers. And that is world public immediately as soon as it reaches a broker. After a night's observing, within 24 hours, we do a more detailed processing of the same difference imaging pipeline and the prompt products pipeline. And within 24 hours, we produce the prompt, or we populate the prompt products database with those data products. And then, of course, we are accumulating thousands and thousands of images, hundreds per night. And so each year, we're going to process all of those, everything in the first year, everything from that year, and then in subsequent years, everything that has been taken up until that point. And we'll have a yearly data release. And so that includes, all the single visits, but also co-added images, so very deep co-add images, and the difference imaging analysis, and various other data products. And so we are going, if you are interested in working with the prompt products and the data release products, the primary way for you to access those is via the Rubin Science platform. And you'll see a demonstration of the science platform if you're not familiar. So the products that are relevant for time domain science include, as far as images, you have the single visit images where you'll have the processed visit image. That's the image with all of the instrument signatures removed. For a single detector, that's currently called a CalX, although that's going to change very soon. But we do, on that, we do the instrument signature removal, photometric and astrometric calibration, and background subtraction, fitting the PSF, all of that. So, and that comes along with each image comes the WCS, the photometric calibration, data quality masks, et cetera. And then the difference images are basically the same, but with the template image subtracted. And then you have catalogs derived from all of these. So the DS source is the difference imaging source catalog, is all of the 5 sigma detections from those difference images. And so that'll have photometry and eventually, detailed astrometry. And then so that's the measurements on single visit images. And then there's the DIA object catalog, which is sort of, think of it as the superset of all of the objects that have been detected on difference images, like to date. So it's constantly growing. And so you'll have summary parameters from all of the source measurements of a given object, all associated with each other, including like statistics of light curves. You'll see a demonstration of that in just a minute. And then another thing we'll do is once we build up that DIA object catalog. We will then go back. We say we know there's an object here at this position. Let's go back to all the difference images that we have taken to date and force a measurement at that position. So that's called the forced source on DIA object catalog. So when will such data products become available to you all? What we're going to release very soon, we're going to be demonstrating using simulated data products right now, but we have already gone on Sky late last year with our commissioning camera, which is just a single raft with 9 CCDs. We observed for about 7 weeks. That's shown in the timeline here, but those data products will be released very soon. Data Preview 1 will consist of all the science quality data that we took during those 7 weeks. That is coming in either June or July. Look for an announcement very soon. We are currently now on Sky with the full LSST camera. And we're in this phase of system optimization where we're doing things like, refining the lookup table for the active optics and various things like that. After a few weeks of that, we will actually start doing what we're calling science validation surveys, and those will make up what will be Data Preview 2. And so that'll be all of the science quality data from this commissioning period of a few weeks. And then we will start the survey late this year. And then the first data release will consist of the first 6 months of that survey data. That'll be data release 1. So this is another way of showing that. This is just showing you here. This is, we're currently serving you the Data Preview 0, which is a simulated survey. The commissioning camera data, Data Preview 1, is coming in June or July. Look for an announcement very soon. And then this shows you Data Preview 2 early next year and mid to late next year, data release 1. And so we will be serving you raw images, process visit images, and the source catalogs derived from them, the COAD images and the catalogs derived from them. And these 2 points are gray because they're stretch goals, but they're likely to happen, that we will also serve you forced source catalogs and the difference images and DIA source and DIA object catalogs. So those are the most relevant for time domain science, but of course it involves having observed enough to build up templates so that you can do the difference imaging. Okay, so then I'm going to demonstrate 2 ways that you can access these data products via the Rubin Science platform. First, I'm going to show you a very quick demo of using the portal, and then after that, we'll move to the notebook aspect and show you how to extract light curves in the notebook. I will note that these are going to be these will move quickly. I'm not going to go through a lot of detail about every line of code that's in the notebook because we have a lot of recordings going through recorded assemblies demonstrating a lot of the basic sort of functionalities and how to use them. So I'll refer you to those for more details about the basics. I'm just going to sort of show you a very rough sort of how could one do science using the data products. I see a question. When will the LSST alerts start flowing? That's yet to be decided, in part because it depends, as I mentioned, it depends on when we are able to build up templates over a large enough area of sky that we have a template available when we observe new images. So it will certainly not be immediately when we start operations, but we're aiming for shortly thereafter. So I won't give you a definite time, but but should be not too far off. Sorry, I can't give you a better answer. There is more language if you go to this RTN 11 document, which is about early science data products. That might give you a little better information. Did anyone have any other questions before we get into doing a little demo? Yeah, Stuart.
Yeah, thanks, Jeff. Just curious, with these PVIs, process visual images, roughly what field of view do you expect that they will encompass? How big were the image stamps or whatever likely to be?
I should know the answer to that, but I don't. They will be per detector, and there are 189 detectors. So, and it's about a 10 square degree field of view. So I guess we can. I can't math that on the fly, but I could, or here's another way of doing it. It's their 4K by 4K detectors with 0.2 arc second pixels. So can I do that math? I probably can't on the fly. I shouldn't trust myself to do it. 13 arc minutes on the side, I think.
Okay, so any individual detector that contains a transient, that full size of that particular detector will be made available. Is that what you're envisaging?
The alert packets actually will only have very small postage stamps.
Right.
Basically, we can only serve,
Yeah,
for the alert packet size. So those will only have, I think it's 35 by 35 pixel postage stamps, but the prompt products database will contain the detector
Okay.
level
Cool.
image. Sure thing. Any other questions before we move into a little demo? I will note also I included in the slide deck, since you saw a lot of links go by throughout the slide deck, there is just a slide at the end here. It's slide 27, I guess, that gathers all of those links for you. Okay, so let's look at some data. This is simulated data from the Data Preview 0, the Desk DC2 Data Challenge 2 data set. So what we're going to go through, you can actually follow this at this link, which I will paste into the chat for you all. I'm going to very quickly go through this demonstration of how to pick out transients of variable stars in the portal. So first thing you want to do is go to data.lsst.cloud. You will land at this splash page, and we want to select the box on the left, the portal. That will take you to something that looks like this. I was already logged in. You may have to log in if you weren't already. That will take you here, and you can see at the top you have these tabs to query images from DP 0.2 or catalogs from DP 0.2 and a few others. Let's go to the catalogs tab. We're going to look for light curves, so we want the catalog data. From here, you can see that you can enter enter coordinates and do a cone search with a radius. You can select which columns you want, but you can also, and you could do that and then say populate and edit ADQL, and it would take you to this window here with the query in ADQL. That's the astrophysics data query language, already populated. But we're going to skip that step just in the interest of time. And we're going to go straight to that. So you can see at the upper right here, where it says view, we're currently in the UI assisted. We want to click on edit ADQL, and we're just going to manually enter the query that we want to make. So I'm going to copy paste this query from this document that I just sent to you. I'm going to copy paste that into this ADQL query box. Here, and I don't know if it'll work properly if I copy paste it into the chat, but we'll try it. It may squawk about the formatting. But what this is doing is getting things within 5 degrees of some sky position. And it's getting things where there are at least 10 detections, 10 dia sources, so 10 detections in different images, so that we're not finding something that just appeared once or twice. We're finding things that appeared repeatedly, and we're getting things like magnitudes and some statistical quantities. And then we click the blue search button in the bottom left. And your query results appear. You can see, perhaps you can see, it's kind of small text, but our query returned 36,322 results in that 5 degree cone search. Now for easier visualization, this is the default. By default, you'll get the table. You can see you'll get this coverage map. It may show that, or it may show this other tab. And you'll get by default a plot of the first 2 columns. We're going to get rid of that in just a sec. But first thing to do to make it easier for what we want to work on is if you go to this menu in the top left, this hamburger menu, you see a lot of options pop up, and we're going to change the layout of our results. So click on this results layout, and I want it to have the tables on the left and the charts on the right. And click on that, that's what you get. Let's go back to the active chart. Okay, so first, if we go back to this, we're going to choose an object that's likely to be a supernova. To do so, we're going to make a plot that looks like this. And so these, first off, we're going to create a new plot by clicking a plus here. And that's going to make a new chart. And if we go back here, this says plot RPSF flux mean on the x-axis and RPSF flux linear slope on the y. So RPS, PS. And you see when I start typing, it sort of auto populates the possibilities here. And so we're going to take this flux linear slope. I'm going to leave everything else at its defaults and say okay. Okay, now we got that plot. And now I'm going to just click the X in this RA-DAC plot because we don't need it. We're going to make it disappear. And we're going to make one more plot. In this one, it's going to be, again, I forgot, RPS flux sigma versus RPS flux mean. Okay, so we got PS flux mean. Oops. Sigma. Okay, so what these are, this is linear slope is just some measure of the slope of some light curve. And this is the sigma of the flux over all of the different images. So these are selected to try and identify supernovae. Basically, the mean flux is going to be 0 because most of the time there's not a supernova in an image and it only appears for a brief time. So the mean flux is going to be near 0. So that's what this swath here is. But then this linear slope will be sort of deviating from the main locus here. So we're positing that these objects in these plumes might be supernovae. And then in this other diagram, this sigma is the scatter of the flux measurements. Again, it's going to typically be near zero because the supernovae are only in a few of the epochs of measurements. And so we presume that this cloud down here might contain supernovae. So if I select one of these objects in this plume, if I click on it, it will select it and you see it highlighted, and you see it's also in this area down here. Let's see what a light curve looks like for that. So now you want to click the tab at the top that says data product, DP02, et cetera, et cetera. When I click that, you see there's this menu at the top where you can retrieve the dia source time series. And I'm going to retrieve all of the bands and all of the information and just click submit. By default, it pulls up a table, but you can click on the button at the top here to switch to a chart view. And that one, to me, does not look like a supernova. Let's try a different one just to find out. Usually, almost all of these, when I click one, come out looking like beautiful supernovae, like that. So you can see it has basically zero flux most of the time, and then it has this brightening and subsequent fade. So, so this is just a demonstration of how you can use some of the statistical quantities that are in the tables to identify transient objects like supernovae. Now, I'm more interested in variable stars. So let's see if we can pick out variable stars with a similar method. So in this panel, I'm going to change the plot. So you can see I've clicked on it, so it's highlighted. And then if I click this little gear at the upper right, that allows me to change the plot parameters. We did extract magnitudes, so I'm going to plot the magnitude on the x-axis and the Stetson J index on the y-axis. And I click apply. I get something looks wacky like that. And then we're going to change on this other panel. We're going to also do Gmag on the x-axis, and I forget which one we used here. Chi-squared, which is another, the chi-squared is the sort of the variation in overall the dia source measurements. Now we're going to do one more thing. This is to show you in the table view here on the left. You can see there's this column G, PS flux, and data. So this is the number of dia source detections of each object. So you can see a lot of them have one or two. Some of them have 30 or more. We want ones with lots of detections because we want a variable star with a nice, well-populated light curve. So in this filter box at the top, I'm going to say I want greater than 30. And when I click that, it will filter my data set automatically. Okay, so now I'm just going to state without proof that the this Stetson J index, most objects, I mean, you can see it here, right? Most objects live sort of in this locus down at the bottom. And when this index is higher, that generally denotes a variable object. So if I select one of these, you can see it's also higher than the main locus in this chi-squared. So seems like it's anomalous in some way. Now let's go and plot a light curve. Now in this case, we're going to instead use the forced source on dia object because a variable star spends part of its time near its mean magnitude, so it will have zero flux in a difference image. So we want the measurements from those epochs as well as when it's above and below its mean flux. So we can get that by extracting the forced source on object time series. And I'm going to select just one band. So we'll just plot G band here and click search. And hopefully we've picked something that is variable. Okay, this is in PSF flux now. So I don't know about you all. I'm not used to thinking in flux very much, but you can definitely tell it's varying quite a bit. Probably a variable star. If you really wanted to see it in magnitudes, you could go in here and convert. Is it plus or minus? I forget. We'll find out. I did it right. That's the conversion from flux and nanojanskis to magnitudes, AB magnitudes. Oh, and then the other thing is to flip the y-axis. So actually, it was better the other way, but no, this is right. Brighter is above. Okay, so this is a light curve of something that's varying by 0.3 of a magnitude. Pretty great. So now you might want to grab all of the measurements for this particular object, download it, and do more detailed analysis on your own. But I'm going to now switch to, so this is, I guess this is showing you that the portal is a really powerful discovery tool. It's a great way to poke around and find, find things. But then for more detailed analysis, you are better off going to the notebook aspect. So if you go back to, I'll just do this directly. If you go back to data.lsst.cloud, the middle box here, if you click on it, will take you to the notebook aspect. I already have it open, so I'm going to just go here. And if you followed the instructions in the slides, you should have a folder called DP1 Sci Prep Seminars, and then time domain within that. And there's this variable star science demo. So let's click on that. And we're going to go through this very quickly because I want to leave time for questions. But basically what this does is something kind of like what we just did in the portal, but it actually uses an isolation forest algorithm to find things that are anomalous in those various statistical quantities. So we'll just go through that a little bit here. Apologize for going fast, but I'm going to get to the fun part. So we're requiring it to have at least 30 data points. And we're extracting a bunch of these statistics. And you can see in this notebook, it tells you what all of these statistics mean to a certain extent. So we're going to, again, do the same search we did, although this time we're using 10 square degrees. And we're applying some color cuts because I'm interested in finding our Lyrae variables, or I guess pulsating variables in general, which are in the instability strip. So they have colors between about minus 0.2 to 0.6 in G minus R. And so that executed, and how many objects did it find? About 7,000. And then we define a couple of other quantities. And then we're going to do this isolation forest algorithm. If you want to know more, there's a link here to tell you about it. But basically, we feed it these quantities, the magnitude, that Stetson J index, chi-squared, the interquartile range of fluxes, and also a couple of the same in the R band, not just the G band. And then we run this isolation forest algorithm, and it does its fit. Basically, again, it looks for objects that are anomalous, and that will run very quickly. And then what we did here is selected the 20 sort of most anomalous objects as classified by that algorithm. So it produces a score that looks like this, and basically the most negative is the most anomalous object. So we selected the 20 outliers at the far end here, and let's plot what they look like in those parameters that we extracted. So here's the Stetson J index and G magnitude on the x-axis of all of these. You see it picked out the things with very high J indexes, with very high interquartile range in their fluxes, meaning that varied a lot. Very high chi-squared relative to most of the objects. So it looks like it did a pretty good job of picking outliers, anomalous objects. So let's look at light curves of just the first 3 of those. And again, this is just the raw flux in time in MJD. You can see this is clearly a variable object, and it's looks like a variable star because it's going both above and below 0 flux. Again, the second one looks pretty variable, and the third one too. So looks like we've done a pretty decent job of identifying candidate variables. The last bit that I want to go through here is just actually running I'm going to go ahead and click start on this because it takes a while. Many of you are probably more expert than I am at this, but I'm running a Lomscargel periodicity search algorithm on these data. Basically, this will try to identify the period, and then we can use that to phase fold the light curve and get a phased light curve for these objects. So that would be, the next science step you would do after having found something that is varying all over the place. You would try and figure out, does it have periodic variability? And so this is just using it's using the Lomscargel implementation from the AstroPy package. And you'll see here, it's using multi-band. So it's using the fluxes from measured in, I think, G, R, I, and Z here, all simultaneously, to look for the best period for each object. I won't go through the details of it, but this is just to show you, something that a user might do. So again, there's the raw light curve in flux. I think it's still going to plot it in flux once it's yes, it is, once it finds one. So this takes a little while to run because it's doing a bunch of Fourier transform stuff thousands of times. So it takes a little bit. So if anyone has any questions, we can take questions while we wait for this to run, and then we can all ooh and ah at the beautiful light curve that comes out, hopefully. Any questions while we wait for this one? Hey, there we go. All right. And sure enough, it found a pretty good period. And you can see this is the light curve in GR and I bands, phased light curve. And it looks like a R Lyrae star. In case you weren't familiar with what an R Lyrae star should look like, let's go to Wikipedia. Says it should look something like that. And sure enough, it looks something like that. You see the steady decline, and then sharp rise and then decline. And the other two, I ran this for 3, so it takes a few minutes to run for all 3. I'm sure there are faster implementations of algorithms like this, but that was where I was going to stop. That was just a quick demo of the types of things you can do with the science platform. Yes, Ilya, I see a question, a hand.
There are several of us who are joining together. Hi, Jeff, and the question is actually from Rio.
Sorry, so this is from the data release or data preview things. What is the difference between what we can do here and what the brokers give us?
So the brokers will give you the alert from I'm trying to recall now what I don't think the alerts come with now I'm forgetting whether they come with I think you'll get the most you'll ever get is the past year of measurements. Whereas once you've reached data releases, once year 3, you could retrieve all 3 years at that position. So I forget whether the alert packets contain all of a year's worth of data, or if it's just the prompt products database that contains the past year. But you won't have all of the measurements, but you should have, I guess the idea is you should have sufficient measurements to classify objects.
Thank you.
Sure. Oh yeah, so my second one finished running. It also looks like a nice variable. Oh, I see a question in the chat. Good question, Lucas. The question is, for those who don't see it, for the data preview, this data preview 0 simulated data, of course, we know the truth because it is simulated. So Lucas would like to know if there's a flag or column where you can filter for specific objects like R. Lyrae or supernovae or things like that. There is. It's a little bit tricky. You have to do some table joining to match to the truth table. But I will, let's see. Oops. But we do have a tutorial notebook that shows you how to do that. Truth tables. So tutorial number 8, truth tables. So you can get to that if you go in the science platform. If you click on this tutorials and then go under GP 0.2, you can load. I may not do it since I'm executing something. Yeah. So this shows you how to do that joining. So you can go and retrieve information for just the types of objects you're interested in. And of course, that's really useful also for testing your algorithms. Like if I did something like what I just did in this notebook, did I identify most of the R. Lyrae, or did I identify 10% or whatever? So yeah. Oh, good, my last light curve. They all look great. Yay. Any other questions? Yeah, Stuart.
Yeah, Jeff, it's curious. I mean, it's great that everything is all sort of background subtracted already, so don't need to worry about that. But obviously then there are lots of cases where flux apparently is negative. But if you try to convert that magnitude, what does that do? I mean, must have to add on some arbitrary amount, well, not maybe not arbitrary, but it automatically accounts for that when you flick to the magnitude scale, does it?
Yeah, it is a problem. You can't go directly from the difference image fluxes to magnitude.
Yeah.
You're right. And so yeah, what I've done is let's see if I retrieved it. I may have it here even. We might be able to do it on the fly. Oh, I didn't retrieve it in my search. Too bad. But no, I'll just tell you. So this has the mean, oh, I did retrieve it. Okay. What's called G tote flux mean is the flux measured on the direct image, not the difference image. So what you could do is you could take that mean flux and add it to those fluxes, and that would get you the variation about the mean magnitude.
Right. Okay. Get it. Thank you. Yeah.
Yeah, so that's it. That's what I would do is I would just add this in and then you can use the AstroPi units to convert from nanojanskis to AB mags then directly. I'm glad you asked actually, because this table, it's good to highlight that this table doesn't, or not only includes the force source measurements on where am I? If I go back here, where I retrieve those. Okay, I'm not. Oh yeah, I am retrieving. It includes not only the force source measurements on the difference images, but it also includes force measurements on the direct images. So you have both available to you when you retrieve these objects. Oh yeah, I see another hand from Arash.
Thanks, Jeff. That was really helpful. One small question I have is regarding the limit of ADQL queries that they typically have, like, I don't know, in the thousands or millions. And what I was wondering was, so what are your advice if if your query is gonna return something very large, given that, like, if this is run on LSSD cloud, what are your advice and what are the hard limits?
That's a very good question. The hard limit is something. It's actually not based on the number of results, but on the volume. So I think it's something like 1 gigabyte or something. But it will, if you hit that limit, it will fail quietly, which is very annoying presently. But I know the database team is working on developing tools that will warn you when you submit the query, hey, that's going to return millions of results. Maybe you want to break it down a little bit. So that is one thing that is coming. But the other thing I would note is, you can do things, I guess, certainly when you're just experimenting, you should maybe query just a small area of sky, for example, until you've sort of honed your query to exactly what you want, and then you can search larger areas. But the other thing that's really important is our databases are sharded spatially. So basically by spatial position, so that any search that uses the spatial positions will be the most efficient. And so you can see here, I included the spatial constraint where we searched within 10 degrees of some sky position. And we recommend that you always include a spatial constraint, if at all possible, to make your queries run optimally. So that's one thing to keep in mind. Of course, there are some queries you might make that a spatial constraint doesn't make sense, but it is the way to get the most efficient queries. Hopefully that answered your question. Thanks. I see we're about to reach the hour, but I'm happy to take any more questions if anyone has. Yeah, Lucas. I see that you unmuted, but we're not hearing you. No, it seems like you're having technical difficulties. I'm not hearing you still.
Can you hear me now?
Oh yeah, that works.
Okay, great. I just have a question regarding the ADQL query. Does the ADQL query of the data portal return error messages as well, in the sense of like where your syntax is wrong and stuff?
I honestly don't know. That's a good question. Well, what if we try it? If we go back here and I mean, I just typed an X into there and we'll see if that returns an error message. Oh, yeah, there we go. So it did.
Okay, good. There's a description as well.
Column non-alias. That
Okay.
column exists. So yeah, I haven't experimented with that much, but
Okay, thanks.
yeah, thanks for asking. Well, thanks everyone for being here. Everyone's free to drop off. I know we're at the hour, but if I'm happy to stay for a few minutes if others have questions. But thank you all so much for attending. Hopefully this was helpful, and I'll post a recording of this session in a reply to the announcement on the community forum very soon.
Yeah, thanks a lot, Jeff. And look, we'll make that recording available on AL's Rubin website, and along with some of the notes that you provided and things like the slides I'm sure will be very, very helpful. And as you may know, just under a month from now, we'll be having a hands-on workshop in Melbourne covering many of the capabilities of objects in DP.2, not just variable objects, but I think it's been a really good introduction to the way that variable objects can be found and handled in Rubin data. So thank you very much for that and for making yourself available, especially at this time for our community. It's been really promising. So thank you for that. And we're really, really excited and looking forward to first look and followed soon by DP1, of course.
Yeah, and look for announcements about both of those very soon.
All right, well, with that, thank you everyone for joining us today, and we hope to try and schedule some more of these in Australasian-friendly times as we get closer to real Rubin data. Thanks, everyone.
Yeah, do reach out to us anytime. We're happy to schedule more.
Cool.
Thanks all for being here.
Bye.